Thanks, Ilya. I really appreciate the invitation to come here and talk. So I'm going to be discussing some recent work coming out of my and the Ram Krishnamurthy's lab. It's a collaboration we've been working on for over a decade, and we've had some exciting results over the last couple of years and some new work that's going to be coming out fairly soon. I just wanted to start the talk by introducing some of the sort of classical dichotomies in the field. This idea of trying to understand the origins of life through a top-down approach of trying to looking at modern biology and drawing it back, or looking from a bottom-up approach, taking some small molecules and seeing if we can heat them together and generate something interesting. And all these kind of models have their advantages and disadvantages. Like biology is a powerful entity, right? It's hard to take a biological system and just throw it in water without its powerful enzymes and cofactors and get it to do something interesting. Chemistry, well, it likes to go to brown goo, as all organic chemists know. It's hard to take a single molecule and get it to do some controlled specific chemistry that doesn't result in just a large mix of tar-like products. The field's also been, I think, long-term divided in this idea of RNA world versus metabolism first. And I think that's something else that we're trying to press, that those things really aren't so different. We're really all looking for chemistry that's sustainable. And that can generate molecules of function. And it just comes down to how do we define then that sustainability and that origin leading to that function. So within that, I view the chemistry that I'm going after as one of looking for these proto-metabolic precursors of modern metabolic pathways, but not being handcuffed to modern biology. So let's look for light inspiration from biology without imagining that we can reproduce that biology exactly in an early biotic world. And I think one of the metaphors that at least works for me is this idea of, let's look at a modern US interstate highway system and imagine how that modern system came about. And we can trace it back to these earlier pre-interstate systems, and even earlier than that to wagon trails. And we can see that there's a great deal of overlap between those first wagon trails and a modern US interstate highway system. And we can learn quite a bit about what the challenges of those wagon trails were by looking at the modern US interstate highway systems. But again, if we're going to apply this to metabolism and what can we learn about early proto-metabolism by looking at modern metabolism, let's make sure that we understand there's some differences. There's modern inventions, and in this metaphor, it might be asphalt and big tunnels and bridges. And there's persistent challenges, those challenges that we can see now and probably represented challenges that were there early on, and solutions to those challenges were found. For example, challenges of topology, finding passes, for example, and passing by population centers. So we're looking for the same things in modern metabolism. We want to look at something like the citric acid cycle and say, all right, from the challenges we see in the citric acid cycle, what can we learn about maybe these earliest proto-metabolic reactions? And we know that there are modern inventions like very available and very specific redox reagents that were very unlikely to be available in the early biotic world, and efficient and sophisticated enzymatic systems. But there are also persistent challenges that the solutions that were found early on probably persist to today. And some of those are things like carbon-carbon bond formation. We know that nature is just a great organic chemist, right? It's not finding new ways to make carbon nucleophiles and carbon electrophiles. That's just good organic chemistry. And if we can follow some of those solutions that we see in modern metabolism, it's very likely that they're following the solutions that were found a long time ago, just like following those passes through a mountain system. And we're also looking for these proto-metabolisms that are compatible with conditions that are sustainable and that can lead to function. And what I mean by that is aqueous, mild aqueous conditions. I want to see a proto-metabolism that can generate plausibly functional biopolymers that can fold, who, when they find these folding motifs can persist as functional catalytic entities in a continuous pathway to modern biology. So I want to see that they are that we're working under common conditions that we see in modern biochemical systems. All right, so some of the things that we think about are, all right, if we're going to constrain ourselves to mild aqueous conditions that are compatible with what we think the function of early biopolymers were, and if we want to try to avoid organic chemistry that leads to tars, like those early bottom-up reactions, we really got to start thinking about those constraints. And the constraints in particular, as an organic chemist that I see, are carbon-carbon bond formation and finding good carbon nucleophiles. And I like that as a constraint as an organic chemist looking at this topic of prebiotic chemistry, because I know how hard it is to find a good carbon nucleophile, and I know how few solutions there are. If I want an electron-rich carbon, and I need one, if I want to form a carbon-carbon bond through non-radical, mild aqueous chemistry, I need some things that are going to stabilize an electron-rich carbon, and there are not that many motifs. We have things like enols and enolates, and potentially, sp hybridized carbons like nitriles as our carbon nucleophiles. And our carbon electrophiles are pretty limited as well. We have things like aldehydes, for example, and potentially thioesters and esters. But something we're looking for a good carbon electrophile in our aqueous system, it is that it's hydrolytically stable. That's a real challenge, right? Finding something that is not destroyed by water. And again, I want sustainable and persistence in my carbon-carbon bond formation. All right, so that's the background of what we're looking for. And we can look to biology for inspiration here. And biology, of course, as an organic chemist, loves carbon-carbon bond formation. And there are some good examples of it out here. We can find examples in the glyoxylate cycle, for example. And here's just some enol, enolate carbon nucleophiles, right? There's not that many options. Biology has found the good one. Reacting with a great electrophile like glyoxylate. We can find it in gluconeogenesis, same sort of motifs, right? Enol, enolate chemistry as our nucleophiles, aldehydes as our electrophiles, fatty acid biosynthesis. Here we're using a thioester as our electrophile, but it's the same sort of chemistry. And we see that throughout biology, using a fixed number of carbon nucleophile motifs and a fixed number of carbon electrophile motifs. And it's those solutions that we see in modern biochemistry that we want to bring back and say, okay, are these the same solutions to some early problems in getting a sustainable protometabolism going? All right, so that brings us to the experimental chemistry. And our current project started off quite a while back, and we were looking at diketopiperazines. These are these cyclic dipeptides. And Ram and I had a really interesting result looking at these diketopiperazines. And we found out that they would tautomerize and hydrolyze to form two keto acids, glyoxylate and pyruvate, if we started from a glycine, cysteine diketopiperazine. And what was wild about that was what we saw in the NMR. And it was a compound that we now call HKG. This is this 4-hydroxy-2-glyoxylate, which is what we saw when we did the hydrolysis of this reaction. And this is exactly the carbon nucleophile in pyruvate, this great carbon electrophile in glyoxylate. In the Center for Chemical Evolution, which I've been a part of for a decade, we love this electrophile. Not only is it really reactive, but it's hydrolytically stable. And these two react together under neutral conditions, mild temperatures, to give us this carbon-carbon bond formation. And that was kind of chemistry that we wanted to follow. And so I'm going to show you a scheme, and this is our Nature Communication paper that was published in 2018. And I just want to show you sort of the outline of the chemistry we were looking at and how rich this chemistry can get. So here is that reaction of pyruvate and glyoxylate to generate that HKG. And we initially looked at this chemistry by throwing in some redox reagents. We know that modern biology is really redox driven. And so we threw in hydrogen peroxide into this reaction. And we saw a series of oxidative decarboxylations, oxidations, followed by a series of aldol chemistry that took us through this rich chemistry that generated a lot of citric acid cycle-like intermediates. And all this was under mild conditions. And again, this is just two starting materials, right? Pyruvate and glyoxylate with one oxidant, plausibly prebiotic hydrogen peroxide. We could also show that you could introduce nitrogen into this chemistry. For example, we could generate aspartate out of this reaction chemistry. And also we could show that it had some metabolic-like potential to it. In other words, we could cycle around this reaction. So let me show you what a little of the data looked like from this. So here's an NMR of this reaction. And those of you who run NMRs will quickly see how clean this chemistry is. When we throw in pyruvate and glyoxylate, we get very, very clean chemistry. And this chemistry stays clean over a wide range of conditions. So here's from slightly acidic to quite basic, just generating primarily this HKG. And then as we start to run this reaction through this rich chemistry, we can follow it doing cycles. So as I mentioned before, we could cycle around what we call the malonite cycle here, and we could follow that just by throwing in labeled glyoxylate. We could watch that label be incorporated and then spread throughout that malonate product they were generating. And then you could see that here through that mass spec data. Okay, that took us to the second phase of this project. And in this reaction of pyruvate and glyoxylate, we saw a triplet in that reaction chemistry. And again, this is proton NMR. And it took us a little while to figure out what that triplet was. And there, in fact, there were a pair of triplets here and here in the proton NMR. We eventually realized what that was a molecule called alpha ketoglutarate. This is a molecule of the citric acid cycle. And you can see a comparison of HKG to alpha ketoglutarate here to here. And what's wild about that transformation is it's a reduction. And reduction is a really important reaction in biology, right? Think of things like the reductive citric acid cycle. And remember, there's no reductant in this reaction. In fact, there's no oxidant at all. This reaction to generate alpha ketoglutarate had only pyruvate and glyoxylate in there. And we could generate through HKG to this alpha ketoglutarate. Ram and I found the mechanism of this reaction, and it was twofold. There's a Cannizzaro-like reduction coming from glyoxylate. So we get the hydrate of glyoxylate that donates a hydride to the dehydrated HKG product we call fumarole formate that got reduced to alpha ketoglutarate. We were also able to show that there was another mechanism that went through an aldol and a retroclason to generate the same alpha ketoglutarate product. And we can see the side products of both of those reactions. So what's kind of wild here then is we have glyoxylate not only acting as a carbon source under these mild conditions, but it's also acting as a redox reagent under the same conditions. So we pushed on this reaction a little bit harder. So here's our pyruvate with our glyoxylate to HKG. We recognize this becomes fumarole formate. If there's more glyoxylate in there, we get that alpha ketoglutarate. Alpha ketoglutarate also reactive with glyoxylate, forms isocitrate formate that then eliminates to a connitoyl formate. And we name these in a very suggestive way because they are just the alpha keto acid versions in order of the reductive citric acid cycle, which I've drawn below: malate to fumarate to succinate to alpha ketoglutarate to isocitrate to aconitate. We got that reaction chemistry in order, but just with the alpha keto acid variants of it. And there's good reason that this citric acid cycle chemistry doesn't occur in water, right? These carboxylic acids, they're inert, right? They are not, the building blocks of these are not good nucleophiles, not good electrophiles. But if we have the alpha keto acid variant of them, we have an alpha carbon here with a hydrogen that's very acidic as compared to what we would have with a carboxylic acid. And it's really the acidity of this keto acid, which is the magic of this chemistry. These alpha keto acids are really just supercharged of these organic acids, right? Good nucleophiles at this alpha carbon, great electrophiles at this keto acid. And so that enables some really interesting chemistry. We can get that aldol chemistry, we can get Claisen-like chemistry, and we can also see things like dehydration in water. So we go from our reactions like HKG to fumaroyl formate. We get these kind of dehydrations occurring in good yield in water, generating this extended conjugation that's thermodynamically favorable of this enone between this double bond and this carbonate. Okay, I want to show you an NMR of what this looks like and also show you some yields. So here is a NMR of pyruvate plus the glyoxylate. And down on the bottom, I've just started, it's the same reaction, I've just started it from alpha ketoglutarate. And in both cases, you can see all of the intermediates, right? This fumaroyl formate from that HKG to the alpha ketoglutarate. We can see the isocitriol formate here, the aconityl formate there. I can see it in higher yields if I start from the intermediate, this alpha ketoglutarate. And here's what some of the yields look for of this reaction, and the conditions are down here. Mild aqueous conditions yielding, generating large yields of these citric acid cycle-like intermediates, just the alpha keto acid versions of them. And we can watch this reaction progress. So here's an HPLC of the reaction of oxaloacetate and glyoxylate. And you can see the generation of fumaroyl formate right here. And this is over time. This is a 72-hour time course of this reaction where it's growing in and then starting to drop off as we're going around this pathway. And here's aconityl formate. I'm highlighting these two because they're easiest to see by UV just because of that conjugated system. But it's kind of wild that you can see now this reaction progressing. You can see a nice time course of the reaction. And again, we could get yields from this HPLC just like we could get from the NMR. All right, so here's our reaction chemistry, right? That pyruvate and glyoxylate. And here is the canonical TCA intermediates. And what I can do is I can take our reaction product and I can throw in some hydrogen peroxide and I can get you an NMR tube full of citric acid cycle intermediates, right? With a little hydrogen peroxide, I can convert all of these keto acids to all of the canonical TCA intermediates. And what I want to make it a point of is that's not all that interesting to me, right? Although these are the intermediates of the modern citric acid cycle, I don't like them as intermediates in an early protometabolism. These intermediates are inert. They're at least inert to do the kinds of chemistry that I want to happen under mild aqueous conditions, where these keto acid variants of them are very active, right? It's selective, it's clean chemistry, but it's chemistry that progresses in high yield under mild conditions. But still, right, from a historical perspective, it's kind of neat that I can take just pyruvate and glyoxylate and at some time period, drop in a little dilute hydrogen peroxide and have a round bottom flask full of citric acid cycle intermediates. Okay, so one of the points I want to make is we've often been looking at taking modern biochemistry back by looking at a modern cycle and seeing if we could reproduce the catalysis under harsher conditions. And however you want to define those harsh conditions that are meant to replicate what modern enzymes can do. And what we've done with this chemistry is instead of trying to find analogs of the enzymes, we found analogs of the intermediates. Right, so the alpha keto acid variants here. So now that we didn't need those harsh conditions, we didn't need the modern enzymes and modern cofactors to get that reaction chemistry to go. All we had to do was, well, charge up a carboxylic acid to its alpha keto acid variant, which was easy to get to. The two smallest alpha keto acid building blocks gets us all of those alpha keto acids. And just to make that point even stronger, so here is the intermediates of the modern citric acid cycle, right? They're poor electrophiles. Carboxylate's a pretty terrible electrophile. They're poor nucleophiles. Trying to generate an enol or an enolate alpha to a carboxylic acid is difficult to do. So let's not use those intermediates and just try to push on harsher and harsher conditions to get them to do the chemistry that we want. Okay, so that leads to just an overview of the chemistry that we've got. So I wanted to show you just a comparison of some of the modern biochemistry. So on the outside here is the citric acid cycle. you might recognize some of these. So the reverse citric acid cycle, malate to fumarate to succinate to alpha-ketoglutarate, isocitrate, aconitate, and so on. And then the glyoxylate cycle, which is using many of the same intermediates, but instead of using CO2 is using glyoxylate instead, which is a really interesting modern biochemical analog to the kinds of chemistry that we're seeing in this alpha keto acid pathway, which is using also glyoxylate as an electrophile, but now replicates that RTCA cycle while skipping over, let's call it, some of those really catalytically difficult steps, like a reductive carboxylation, for example. But we can generate now that same kind of chemistry, fumaroleformate to alpha-ketoglutarate to isocitrate to aconitoyl-formate. And there's some interesting parallels to think about. So for example, in the modern citric acid cycle, there still are alpha keto acids, right? There's this alpha-ketoglutarate right here. There's the oxaloacetate up here. And we can start to think about why modern biochemistry might have kept some alpha-keto acids around. And a real good reason to do that is core to modern biochemistry is this transformation between keto acids and amino acids. Reaction of this amination between the keto acids and amino acids is a wonderful source, then synthetic source of our amino acids from alpha keto acids. And so it might explain why a few alpha keto acids remain, just a biochemical source of subsequent amino acids. We might ask also, why does the modern citric acid cycle use what I've been calling are these inert dead intermediates, these carboxylic acids versus these alpha keto acids? Well, not to anthropomorphize this too much, but if I was an evolving chemical system that started to generate good catalysts, it's exactly what I would want. I would want inert intermediates that I could control kinetically versus these much more active alpha keto acids. So we can make a lot of sense from that as catalytic efficiency increased. There might have been a driving force from the keto acid to their oxidized, more inert products here. Okay. So I just want to bring up a quick quote here from Leslie Orgel. And he mentioned a couple of decades back that the chance of closing a cycle of reactions as complex as the reverse citric acid cycle, for example, is negligible. And the first thing I want to say is that we absolutely did not, right? First off, we're not doing the canonical citric acid cycle. Second off, although we tried for a year to close it, we weren't able to, right? We went all the way around, but weren't able to close that last step. But what I do want to bring up is how unexpected I think this chemistry is and how simple it is. It is RTCA-like, and it does start from just two molecules, right? Pyruvate and glyoxylate in water under mild temperature is all it takes. And this chemistry was, let's call it hidden, right? It required just taking two very well-known molecules and following them along. And it's one of the things that in our collaboration we're really pushing is this idea of following the chemistry. There's lots of wonderful, undiscovered, and productive chemistry out there in this proto-metabolic space to discover. So just briefly, what's next? We're really interested in bringing nitrogen into this world, taking these alpha keto acids to amino acids and taking these amino acids onto nucleobases. And our collaboration has two papers in review right now. One that is using alpha keto acids and hydantoins to generate high yields of these of nucleobases, and another using alpha keto acids to generate hydantoins and then onto amino acids. So in the short term, keep your eye out for both of these papers. There's lots of what we think is neat chemistry coming out in the short term. So I want to thank what has been the greatest collaboration of my career with Ram Krishnamurthy and the Krishnamurthy Lab, particularly Mahipal and Jaya. And my lab is run by undergraduates. A great deal of the chemistry you just saw was run by Trent and Rachel and Julia as well. And so this has been a really productive area for us, for undergraduate research, and for this collaboration that's been part of the CCE for 10 years. So thank you for your time and attention, and I look forward to taking your questions either now or in the break.